Thank you very much, Brian, for your kind introduction, and welcome to everybody. So Lucas gave a great talk about the OpenMP parallelization of FTS. I'm going to talk about the MPI parallelization of FTS now. I'm not a fire protection engineer, I'm a mathematician, and I will try to give some numerical insights into the parallel solution of the FTS pressure equation with a special focus on scalability and accuracy. So first, a small overview. I will start with the explanation of some very special characteristics of the FTS pressure equation, and then I will present two different approaches for its parallel solution. I will present two numerical examples for it, and then I will draw some conclusions based on those tests, and finally I will give an outlook. So, let me begin with the characteristics of the FTS pressure equation, which should make clear why it is so important to have a very special look on this equation in the context of an efficient parallelization of FTS. Here you can see the pressure equation, how it is used in FTS. The details don't matter, but what is important to know that from a mathematical point of view, this equation is an elliptic partial differential equation of Poisson type. It's a very important component in the complete solution process. This term f contains a lot of source terms from the previous time step. So this equation is strongly linked with the computation of all the other required quantities in FTS. And the solution to this equation strongly influences the quality of the whole simulation. So in order to run a fire scenario on a computing system, we have to make it finite somehow. We have to bring it on a grid. And in FTS, this is based on the use of a finite difference discretization method. It's shown here for the single mesh case. This method is based on the use of a discretization stencil, which is cell-centered. And this stencil somehow specifies the relations of the single grid cells between each other. And at the end, you get a linear system of equations of this type. But now, we do not want to solve single mesh problems. We want to solve multi-mesh problems. And to this end, the computational domain is split up into a lot of different sub-meshes. And so we do not end with one system of equations, but we end with, let's say, m linear systems of equations. And those different meshes may now be assigned to the processors of a parallel computer. But a special care must be taken along those internal boundaries which arise in the subdivision process, because we do not want to solve m separate problems. We want to solve for the global problem, and therefore we have to exchange data between those meshes to make it global. Elliptic equations possess a very high velocity for the propagation of information. And this means that if you have a new local information somewhere in the domain, let's say a new inflow condition, then this data spread immediately across the whole domain. So local data have impact to the whole solution. All in all, you have a very strong global coupling. And this has some consequences for the multi-mesh solver, because it must be able to reproduce this fast spread of information somehow. We get a very high level of fragmentation by the subdivision process. And the multi-mesh solver must be able to compensate this fragmentation somehow. So in the best case, it should reach an approximation quality which is somehow comparable to that of a corresponding single mesh case, if it is available. Okay, based on this background, I would like to present two different parallel approaches for the FTS pressure equation now. And I will explain both by the aid of this very simple pipe-shaped geometry, which I like very much because it allows for a simple graphical visualization of the underlying concepts. And I will use a subdivision into 4 single submeshes for this grid. And you will see this grid again, you will see this grid again in the next slides in different shapes. So let me begin with the official current approach, the multi-mesh FFT. This one is based on fast Fourier transformation. It's a locally working method, which is embedded in an additional iterative averaging process along internal boundaries and solid obstructions. And by construction, it doesn't solve the same system of equations as a corresponding single mesh solver would do if it was available for a given geometry. So here you can see how it works graphically. We have our grid, and on each submesh we perform a local FFT method. And those local meshes are coupled together with local data exchanges. That means each mesh has only to talk with its direct neighbors. And on modern parallel computers, this operation can be performed with high computational efficiency. And additionally, we have a surrounding iteration which is responsible to make the single meshes match along internal boundaries. So all in all, we have a very high local efficiency with the FFT solutions, but we only have a slow transport of global information because data exchange works only locally. So a new information can only be passed stepwise through the domain. And it's usual for an iterative process that we also need a stopping criterion. And for this iteration, you have to specify a velocity tolerance, and you can also specify a maximum number of iterations. And this velocity tolerance specifies how good the normals of the different velocity components have to match at an internal boundary. So if you don't specify anything, then some default values are taken. But it's not so easy to find an optimal choice for this velocity tolerance at all. So if you specify it to cos, then you get an insufficient accuracy. If you specify it to fine, then your computational time might be very high. So you have to find a good compromise there. Well, the second approach is called scalable recursive clustering, or in short, ScaRC. This is really a globally working method, and it combines domain decomposition techniques with multi-grid methods. And the term multi-grid shouldn't be interchanged with the term multi-mesh. We will see it on the next slide because it is related only on one mesh, but with different grids for this single mesh. So in contrast to the FFT method, this method really solves the same system of equations as a corresponding single mesh solver would do. And here you can see how it works. This is the geometric multi-grid variant of it. There are some other classes of this method. In this variant, we have a complete sequence of grids with different grid resolutions, and we have efficient interpolation operators between those grids. And all those grids are again coupled together in an iteration process. On all the different grids, except of the closest one, I only need local and cheap data exchanges. But only on the closest grid one level, I also need global data exchanges, which seems to be somehow unavoidable to me because I want to reproduce this very strong global connectivity. So on the first side, this looks much more wasteful than the FFT method, yeah, because I have to use more levels. But on the other hand, each level covers a different range of the global information flow, so that we get a very strong global coupling and a much higher accuracy, as we will see. I already mentioned that there is not only the geometric multigrid variant, I also have an algebraic multigrid variant, and both classes only differ in the way that they compose the single components of the solver. Yeah? And whereas the geometric multigrid class, it's easier to implement, works very good for classes which are somehow regular. The algebraic multigrids are something like the race horses under the iterative solvers for huge systems of linear equations. And they also work for more general and irregular problem classes. Okay. Now we have all ingredients to perform some numerical tests. And I will start with the test case ScaRC 3D, which is about frequently changing global behavior. It's just the generalization of the already existing test case ScaRC 2D, which is part of the verification directory. It uses a simple cube-shaped domain in 3D with a grid resolution of 128 in each direction. And we have different inflows from 3 sides, different in size. And additionally, those inflows are changed in small time intervals, triggered by ramp functions. So there is no steady state at all in this domain. We have steadily changing situations. And therefore, this is a great challenge for the different solvers. Now, I wanted to know if both pressure solvers are able to reproduce this fast spread of data. And to this end, I defined a pressure device somewhere in the middle of the domain, and I used different subdivisions for it, namely in 64 meshes and in 512 meshes. So this is not the fine grid, this is the subdivision. And I compared the cost of the pressure device in this point for the single mesh computation with that of the different multi-mesh computations. Well, here you can see the cost of the single mesh pressure device. And it's very stepwise, it has a lot of jumps, and each jump corresponds to a time when the inflow conditions were changed. And additionally, you can see a lot of oscillations. So it shouldn't be easy to reproduce that with the multi-mesh solvers. Here you have the whole situation. You see the comparison of the single mesh case in red. So different tolerances for the multi-mesh case and with ScaRC. Let's begin with the blue line here. This is the multi-mesh FFT in its default version. So you see there is no correspondence at all. It's not able to reproduce the global connectivity. The green line corresponds to 10 to the power of -2, which is bad too. A first approach can be seen for the magenta line, which corresponds to 10 to the -3. And the best result is obtained for the cyan line, which corresponds to 10 to the power of -4. But if we now have a detailed look on it, on this special area here, then you can see, well, the cyan line is quite good, but it doesn't really match the single mesh course. The black line here, the black dashed line, is obtained with ScaRC. So you can see ScaRC is really able to match all those oscillations and this big jump. So please keep in mind that the cyan line corresponding to 10 to the -4 is the best one for the multi-mesh FFT. So you can see here the desired number of pressure iterations, which is required to reach this tolerance. And as we see here, we have a drastic increase in the number of pressure iterations and a corresponding increase of computational overhead. Yeah? And additionally, you can see those special peaks here. These are the times when the inflow conditions were changed, and we have an additional increase here, reflecting the fact that the FFT method really has trouble to catch global situations in time, global changes in time. So please have a last look at this picture. I will show you the corresponding picture for 512 meshes now. There we have this situation. So you can see there is less white in this picture. The default version and the coarser velocity tolerances are more bad. So you can see the more meshes you have, the bigger the differences are. And finally, I will show you a comparison of the computing times for all those different cases, measured for the 512 mesh case. This is the computing time for ScaRC. This is the default solver, the big, the medium tolerance, and this is the fine one. And in fact, ScaRC needs more time than the default FFT solver. But if you be fair, you can only compare those computations, because this one is the only one which produces a comparable accuracy. Yeah. Okay, this was my first test case. Now a short second test case. It's about SHAN3 from the verification guide, and it's called Variable Density Manufactured Solution. There is a constant velocity field from the lower left to the upper right. And there, this case is treated as a single mesh case with different grid resolutions. And for some quantities, the analytical solutions were known so that a convergence study could be performed. And for the single mesh case, this study clearly showed the second order convergence of the FDS time stepping scheme. And now I wanted to know if ScaRC is able to reproduce this result even for the multi-mesh case. So I subdivided the domain into 4 and 16 meshes. Here you can see the whole simulation. If it runs, yes, it does. So there is no obvious difference between the simulations. And similar to the single mesh case, I did a convergence study. I measured the L2 errors for mixture fraction, density, velocity, and pressure for the different grid resolutions here. And what you can see here is the reference line for second order convergence. And both pictures look very similar to the single mesh case. So there is no obvious difference. And ScaRC is really able to keep the second order convergence for both subdivisions. And in fact, it should, because it solves the same system of equations. Okay, now some final conclusions based on those tests. Yeah, the advantages for the FFT are clear. The local FFT solvers on the single submeshes are extremely fast and robust. They have a very high local efficiency. I will never be as fast as that with ScaRC. On the other hand, the FFT method has trouble to catch global effects in time. There is always a delay if you have a lot of submeshes. So the scalability with respect to high numbers of submeshes is questionable. And it's not easy to find optimal values for the velocity tolerance. And there may be many, many pressure iterations to reach a fine tolerance. And usually, there are differences to a corresponding single mesh case if it is available. In contrast to that, ScaRC really shows a better accordance to the single mesh case and a higher approximation accuracy. And especially, it has much better scalability properties with respect to higher numbers of subdomains. Disadvantages, I also have to choose some parameters, a stopping criterion, yeah, which may be difficult too. And computing times are mostly higher at the moment than for multi-mesh FFT, at least for coarser tolerances. Yeah. So there is still a lot to do. Now let me give you a final outlook. I intend to do some further optimizations. In the moment, I'm in the process of improving the algebraic multi-grid variant of ScaRC. And I try to include concepts for the use of mesh-wise different grid resolutions. And sure, I want to improve the runtime behavior. I also plan some further verification tests where I analyze separated physical phenomena, in the best case with a known analytical solution. Yeah, and finally, I should do some realistic application tests. So checking the applicability of ScaRC on realistic and very complex geometries. Okay, now I've reached the end of my talk. Yeah, and happy to answer questions.
Thank you. Questions for Susan? Randy?
Hi, Susan. So very nice talk.
Thank you.
But I have to, I have to defend my territory a little bit. So you've presented two cases.
Yeah.
Okay. The first case, I will agree with you. We've known for quite some time that it is easy to break the current solver, and you guys, being very smart, know exactly how to break it. And the way you break it is by changing initial conditions abruptly. Okay, so everybody shouldn't panic in here that if you have a steady state fire, those are not the kinds of results that you get. Okay, so that's the first comment that I'd like to make. I'd also like to make the comment, for example, in a lot of my validation cases that I have set up, okay, the comment was made earlier by Lucas, I believe, that you can't put mesh interfaces within a fire or above a fire. That's not true. Everything works fine, okay, as long as it's a steady inflow. Okay, you can get very good statistically stationary results because, as you pointed out, the pressure solver can eventually catch up. Okay, the current solver can eventually catch up. If you go in and you add these stepwise changes to the inflow condition on a time scale in which our pressure solver can't catch up, you are going to see the garbage that you showed in your first test case. Agreed, we understand that, and that's why we're so supportive of your work to fix it. So I want to make that point clear as well. On the second test case, you sort of gave the impression that the current, the Shun test case, you gave the impression that the current pressure solver couldn't do what you were doing, and you gave the impression that what we have in our verification guide is a single mesh solver. True, it's a single mesh, but it is a periodic boundary condition with an interpolated boundary, so it might as well be an infinite number of meshes as far as FDS is concerned. Okay, so our basic default pressure solver is performing as if it's a multiple mesh test case. In that case, it is not using periodic boundaries for the FFT solution. So so
we have to talk about that.
We can talk more about that, but my only point is that it's good that ScaRC can do that. That's a verification case, but we also do that in the current
but not in the multi-mesh version, only in the single mesh one.
There's one mesh, but it is a periodic boundary. Yeah, but I'm not using a periodic matrix to solve that Poisson's equation. It's an interpolated boundary, just as if we had, a million meshes connected.
But you couldn't run it with the FFT solver, this case, in parallel.
It is. Yes, we could. We do.
Okay, so we have to talk.
Other questions? No? Okay. Well, thank you very much, Susan. That was great.